Hi, so what we're going to look at today is the normal distribution curve and z-scores and everything like that. This is what I would consider the beginning of the hard statistics. So it's not incredibly difficult, but it's something where if you don't have a really good handle and concept of what's happening with z-scores and the normal distribution, then it's going to be fairly difficult going forward. So what we're going to do is I'm going to work through the notes that I've posted online, but this way you can hear me talking, and I have another visual that I can use for you as well to maybe work through some of these things with you. So go ahead and follow along, and hopefully you'll have a better understanding and grasp of what's going on. All right, so we're going to start by looking at and discussing just standard deviation. And so when you think about standard deviation, what's really happening is every data point that you have is being compared to the whole sample that you have. And so what standard deviation does is it tells you the standard or the normal or the average amount that each data point varies from that mean, from that normal. And so what's happening is you're going to take, if this is your normal, this data point, you're going to take the distance from this data point to the normal, then this one to the normal, this one to the normal, this one to the normal. And you're going to average all of those distances together. All of those distances averaged together gives you your standard deviation. And that's super important for normal distribution. And there's a different video that discusses how to find standard deviation and variance on Excel. So you can go ahead and look at that. But here we're going to just assume that we already have it so we can get into the normal distribution. Okay, so standard deviation, again, we already talked about that, but what it's going to do for us in terms of the normal distribution is what it does is it standardizes the performances or the studies or whatever it is that you're talking about. And so, as I said before, it's the distance from the mean. So it's taking every point and standardizing or making the distance from the mean, comparing it to the same average. Your standardized values have no units. Okay, so really it's just a number. It's not that you are 4 feet away or 4 units away. There's no units. It's just kind of there. All right, it's just this number. And so with the standardized units, you take out everything that could possibly be impacting it. So you could compare inches, you could compare feet, you could compare anything really, because now it's being standardized as a whole. Okay. All right. So they have no units, and that brings us to the actual z-score. And so what a z-score is the z-score is the number of standard deviations a data value, whatever it is you're talking about, is from the mean. Okay, so in normal distributions, that's what we're concerned with. So we have our entire sample, and we're going to look at how far away it is from the average to see how unique that value is. And if it's really unique, then that's something that we're going to consider later as statistically significant. And that's what we're going to look at. All right, so going back to the notes, you have this formula, z equals x minus x bar divided by sx, right? Or z equals x minus mu divided by, and then you have your standard deviation, okay, your omega, or your sigma. Okay, and so that's your value minus your mean divided by your standard deviation. Your value, that is the data point you're looking at. Okay, so your positive z-scores are going to land above the mean, and your negative z-scores are going to land below the mean. Which makes sense, right? Positive versus negative, above versus below. All right, then with that, all of these z-scores make up what we consider a normal model, right? So your normal model is used, and it's only used when your distributions, so remember when we were making our frequency diagrams, so we were making bar charts and histograms and things like that. So in our distributions, before we had bars, when those bars take the shape of being unimodal, so there's one mode in the middle, right? So they have shapes that are unimodal. And they're roughly symmetric. Okay, so we described those before. If they're unimodal and roughly symmetric or approximately symmetric, then you can go ahead and use a normal model, which would be our normal distribution, right? These would be our bell curves. Okay, so it says you must check this before using, which is true. If you make that histogram or that bar chart and it's not unimodal, okay, so it's not making one curve, you can't use the normal model. You're going to have to use a different type of model. And we'll get into that later. Like I said, this is the beginning of the hard stat, so we're going to get into that later. So make sure that it is actually unimodal. Look, I have a fun example. So if it is actually that, then we can go ahead and work with it. Okay, when you talk about normal distributions, they will always have a mean of 0 and a classic standard deviation of 1. That's just how everything gets set up, okay, when you make your graph. This, as a whole, gives us an idea of how extreme a data value is by telling us how likely it is to find a value that far from the mean. All right, so that brings us to the empirical rule. All right, and what the empirical rule says is that in general, based on all of the normal distributions that have taken place in all of the studies over time, anytime you have a normal distribution, so something that's unimodal and approximately symmetric, it's saying that 68% of the values, 68% of your values are going to fall within one standard deviation. Okay, no matter what your sample is, no matter what the population is, in general, based on all the studies over time, if it's a normal model, if it's truly unimodal and symmetric, 68% of the values are going to fall within one standard deviation. 95% will fall within 2 standard deviations, 99.7% will fall within 3 standard deviations. Okay, so that just goes to show that if you are 3 standard deviations away, 99% of everybody else is within here. So if you are more than 3 standard deviations away, you are really unique, okay, which is saying you're super extreme in terms of the data. That is going to give you data points that fall outside of the norm or the regular. All right, so 68% of your values fall within 1, 95 within 2, 99.7 within 3. Right, which is shown on your graph. So when you look at the picture, this is what a standard normal curve will look like, and this is how you are going to hopefully be better able to see and visualize what these values are telling you. Remember, they don't have units. So all you're dealing with a z-score is a number. You have a z of 2.5. Well, what does that mean? What does that even, how does that even relate to your sample and what you're actually talking about? So this will hopefully help you visualize that. So when you look at your picture, your mu is always in the middle. Remember, mu is your average. And when you take your average, what this is saying over here is you're taking mu plus 1 standard deviation. And that would give you, this is a z-score of 1, okay? Because you are 1 standard deviation away from the mean and you're on the positive side. You're above your 0, okay? The next one, this would be a z-value of 2 because you are 2 standard deviations above 0, right? And then 3, and then you can go the other way, where z would equal -1 and z would equal -2 and so forth, right? And it's all based around this mu right here, right? Okay, so how do you actually find those z values? How do you get to those? Okay, so what you're going to do is you're going to use that formula that we talked about up above. And that formula, remember, z equals value minus mean divided by standard deviation. That's what we're looking at. So your value is your data point, whatever data point it is you're talking about, minus the mean of your sample divided by the standard deviation of your sample, right? If it's talking about population, that's fine. You just need to make sure the mean and the standard deviation are both coming from the same thing. Okay, so the mean of the population goes with standard deviation of the population. You can't have mean of a sample and standard deviation of the population, then you don't want to use it. All right, so make sure you're staying with the same thing. Okay, so to calculate these probabilities, that's what we're looking at. First, you have to find a z-score, and then you're going to calculate the probability. Number one, fill in the data values into the formula to find the z-score. Okay. Find the z-score. Step number two, use your chart. You're going to use your normal distribution chart to find the corresponding probability for the value left, or you could say below or less than, the given data value. Your chart, your normal distribution chart, always gives you the values to the left of the value you're talking about. Okay, it gives you the probability to the left of the value that you're talking about. Okay, then you go from there to use that value to find anything that you need, whether it's less than, greater than, in between. Those are the things we're going to look at. Okay, so if you're going to find a value instead of to the left, if you need to find a value to the right or above or greater than, because your problem will state that. So if you need to find a value to the right, above, or greater than a given data value, then you need to take 1 minus that table probability, 1 minus the value you actually found on your table. To find an in-between value, you must find the probabilities for both data points. And then you subtract your bigger table value minus your smaller table value, right? So that will give you the area in between. So again, the numbers on your chart give you the probability that they will occur. They give you the area under that curve, okay? Because area under the curve is 1. So if you think in terms of percentages, what percent are you doing better than or worse than compared to that 1 as a whole? So let's go ahead and take a look at an example so that we can see how the z-scores and the probabilities and the probability table, how everything connects together and works out. So looking at the example, it says at a large department store, the average number of years of service was 13.5 with a standard deviation of 6.2 years. So when you take a look at that, it gives you that average and it gives you the standard deviation. Both of those we need for our z-score formula. Z equals value minus mean divided by standard deviation. Okay? So let's go ahead and write that down first for our part A. Z equals value minus mean divided by standard deviation. Then when you look at part A, it gives you a value of 14 years. We want to look at 14 years. So when you go ahead and take a look at when you use what you're given up above with an average of 13.5 and a standard deviation of 6.2, then you can go ahead and plug into this formula. Okay, so our x, our value, we're going to have z equals our value of 14 minus our mean of 13.5 divided by standard deviation of 6.2. Okay, when you math that all out, you will end up with a z-score of 0.08. Okay, so then if you move over here, we have a z-score of 0.08. Average in the problem is 13.5, right? So we can put that here in the middle because that's where average goes. And if you wanted to label more, one standard deviation, a standard deviation is 6.2 years. So if you have your average of 13.5, plus one standard deviation of 6.2. That will put you at 19.7. So then when you look back at your image, you'll be at 19.7 as one